Hello, everyone. This is Chen Hao from eTeach Zurich. I'm preparing this recording to make up for my oral presentation at the Embodied World Model workshop at NeurIPS 2025, which was unfortunately interrupted. So I really appreciate the opportunity that I can finish my presentation here. So word models. When people think of word models, people normally think of video generation models, and because of the limited number of data, state-of-the-art word models are kind of still used for either generation or for evaluation purpose mainly. We come from the robotic background, and we think, oh, maybe we can use word models as a way to prescribe control policies. So that's why we want to introduce the robotic word model, a neural network, or black box and end-to-end simulator for robust policy optimization in robotics. So we really make our effort in bootstrapping control policy from the word model that really works on hardware. So again, Chen Hao here. I'm from eTeach Zurich. Yeah, if you come from the robotic background, you must be very familiar with the state-of-the-art, say, policy training method, where people just throw the robot in a high-fidelity simulator, of course, identify all the parameters, and then just train people on it. And after that, we deploy this policy on the real hardware and hope to work, of course, with all the tricks of domain realization, domain adaptation, etc. But after deploying this simulator learn policy in the real world, which people normally refer to as sim to real transfer, there's no online, there's no further learning going on. That's kind of waste of data because after deploying this on real world, we could have still collected data, the real world state action pairs, and further fine tune or update the policy based on these data. But then if you want to do this with RL, it's a little bit tricky because we only have really limited number of real data. And for RL, we need a lot of data. So what we had in mind is, of course, well, instead we train a model, a work model or a dynamics model, and with the real world data. Of course, we can pre-train this model in the simulator and fine-tune it on real world to save more data. And after that, we just use this model and generate imagination rollouts to further update the policy. So you can see this is kind of a model-based RL pipeline. And if you're familiar with Dreamer, TDMPC, we're talking about a very similar strategy. So it's fine if the initial model is kind of bad because, well, then the policy is also a little bit bad because you always have the chance to deploy the policy back into the real interactions, collect more data to further fine-tune the model, further improve the policy. So this is kind of an online, continual learning setup. This is a very simple idea, right? But why there has been a very limited success. And so for policy optimization, either if you use, let's say, policy gradient methods or value function-based method, to obtain an unbiased value estimation, we need to roll out our dynamics for long. But this is kind of not very straightforward in a learned dynamics because when you autoregressively roll out your learned dynamics for long, your trajectory will deviate because errors compound. And also, eventually, we want to deploy our policy on the real hardware. A lot of people do domain randomization, but this again not something that is straightforward in the learned dynamics because once you perturb the states or perturb the dynamics, you'll quickly deviate again from the ground truth, and the errors compound again. You'll fly out, and eventually, in terms of lag locomotion, the initial or the original dynamics itself is not continuous, it's discrete. When we switch the contact patterns, switch the lags, the dynamics is really not continuous, but now we're trying to approximate with neural network, which is continuous. So these are kind of the bottlenecks or things we have to deal with. And some people may say, oh, you could have used planning, then you don't have to deal with all this policy learning issues. But in lag locomotion, especially, the planning for now, given a large state action space, is not sufficient enough. It's not efficient enough because we normally run our policy on 50 hertz, and planning is very hardly able to achieve that. And also, even for planning, if you only care about the current reward, like the per step reward, it's fine. But once you care about more like long-term horizon, you still need a terminal value function. So it's actually we're having the same problem here. So the task or the main contribution of this work is really to stabilize the long horizon autoregressive rollouts on the learned dynamics, and which is robust against the perturbations. And then the policy learning part is relatively simple. We just used stable learned dynamics to bootstrap the policy and to control it on real hardware. And also intentionally, we wanted to keep the architecture of the model relatively simple because eventually we want to apply this whole thing on a real hardware where we have only limited data, limited online data. So compared with the very complicated architectures, a simpler architecture will require less samples to update. Great, and the trick is actually very simple and it's task agnostic and architecture agnostic. That everyone can do this whenever they want to learn a say, autoregressive model. So we're trying to, for model learning, normally we have state action and predicting next state. In addition to doing that, you can feed back your next state prediction back into the model and then predict the next state. By doing so, it's all gradient retaining. So when you backpropagate the loss, of course, you aggregate all the loss. When you backpropagate the loss through time, you're accounting for the error not happening only at the current step, but also, the consequential errors accumulated later. So we call this autoregressive training, and some people call it self-forcing. But you can see this is a rather expensive operation because one, this is not very easily parallelizable. You have to wait for the previous prediction. And also, it's all gradient retaining, so memory can take a lot of space. In our case, we figured out that even if we only do this autoregressive forecast prediction for 8 steps, we're able to achieve very stable long horizon rollouts for more than 500 steps, which I'm going to show later. But this is not enough. Another very important trick is for this next state prediction, we're not simply predicting this one single point, but we sample from a distribution. So we're predicting a distribution, in our case, a Gaussian. And when we sample from the distribution, we keep all the gradients using a reparameterization trick. This is kind of important because during training, if we're doing this already, we're exposing the model to the potential errors or noise it might see during inference time. So this really, you can think of this as a noise injection, and this really helped improve the robustness of the model a lot. Great, we test this framework on, I think, more than 10 different environments. Because you can see there's no really domain knowledge or any additional things. We want to try to keep the architecture or the trick as simple as possible, so it can really generalize the different frameworks. We also compare it with the simple architectures like MLP or some other fancy architectures like RSSM using Dreamer or transformer-based method. And here we found out if you train these other architectures similarly using autoregressive training method, they can actually achieve pretty similar performance. But if you only train with one step, which is commonly called as teacher forcing, the long horizon prediction is really bad. Yeah, so I want to show you the stable autoregressive rollout for more than 500 steps. On the left, with the background a little bit reddish, it's the autoregressive pure imagination. So purely autoregressive, there's no ground truth coming in. On the right, we have the ground truth. So you can say eventually they will deviate a little bit, but this is 10 seconds. So we have 500 steps, which is way more than enough in policy optimization. So because it's called robotic world model, it's a general one that can be used on different environments. So here we're showing this. And also, in a lot of model-based RL frameworks, normally the task is very simplified. Like for example, for quadruped locomotion, some tasks is just walk forward or stay alive. But in our case, we try to make this as full scale as possible. So when we evaluate our method, we always compare it with the full scaled task space. In locomotion, for example, it's always the goal conditioned velocity command tracking task, which requires definitely more samples. Yeah. So so we only talked about the model training part so far. So the policy part is very, very simple. If you are familiar with the Dyna training, it's basically doing that. So during policy training, we have some like real world environment interactions, and we can branch off from there and start imagination using our learned word model. Of course, you can do this like like from anywhere on the main branch. So then we use all these imagination transitions to update the policy using model free RL. In our case, we use PPO because PPO is normally the go-to method in Lego locomotion and also is very efficient. And again, now we're sampling from this distributions, which simulates domain randomization in alternative methods. And we especially evaluate our methods on two environments. Above, it's NMOD, and at the bottom is Unitary G1. So yeah, let's see how it performs. So this is our experiment on these two platforms. You can see it's like Omni velocity command tracking on a full-scale task phase. But nowadays, like people are very spoiled by seeing these tasks. There's really nothing fancy, but we are very proud and happy to see we made alternative solutions to, say, like a locomotion with model-based methods. And I promised you, like with the stochastic prediction hat, we're able to obtain very high robustness, which translates from model to the policy. And here you can see we're demonstrating that. Great. So yeah, that's it. Let me quickly summarize. So for the model part, we propose a robotics work model, which use autoregressive rollout to feedback the next state prediction with all the gradients and do the next state. And when you backpropagate through time, and this really accounts for the errors for all the predictions that stabilize for long horizon trajectory rollout. And also we use the stochastic predictions to simulate domain randomization or noise injection during this training process. And in policy training, it's as simple as Dyna style, where we use model-free RL. We have in a paper an evaluation comparison versus the method using first gradient, since we have a neural network model. Also with the domain randomization, we're able to transfer it very well on the real hardware. So we're achieving, let's say, comparable performance with the state-of-art model free training. So that's something we're very proud of. Great. Yeah, that's it. So our work is complete open sourced. You can definitely find everything about the work on the webpage. We have the paper, the code is out there, and we have the videos of different ablation studies. So thank you again very much for this opportunity. And even though the original representation was interrupted by conference people, but still, I really appreciate people who stayed late for me. It was already the last talk, and also after we were moved outside. Yeah, thanks for all the audience in the corridor. And really means a lot to me. It means more than the potential award this has. So great. Thank you very much, and definitely do let me know if you have questions. Yeah, thank you.